Hello everyone, my name is Vitaly Babenko. I am a PhD student from the National Technical University of Ukraine in Kyiv. Today I'm excited to present our research on assessing cognitive workload in UV operators. Our focus is on how we use machine learning and reasoning to take out cognitive overload in real time, ensuring UV operators maintain peak performance during critical missions. The mental workload of UV operators plays a crucial role in mission success. High cognitive workload directly impacts decision-making, slows response times, and ultimately affects mission outcomes. Effective workload management is critical for operational efficiency, safety, and accuracy. Cognitive workload is influenced by various factors, including operator traits, environmental stressors, and task complexity. These factors interact to determine the operator's capacity to manage multiple tasks efficiently and maintain situational awareness. Traditional machine learning models for cognitive workload assessment typically achieve around 70% accuracy, which is insufficient for real-time applications in high-stakes environments. In UV operations, even small inaccuracies can lead to mission-critical errors. To bridge this gap, our work integrates machine learning with Bayesian reasoning to enhance cognitive workload assessment, precision, and reliability. Our approach aims to deliver an accurate real-time cognitive workload assessment system that enhances UV operators' performance by providing timely, context-sensitive insights. By continuously monitoring workload conditions, our model contributes to improved situational awareness, mission outcomes, and operator safety. Our methodology involves three main stages: data collection, machine learning, and Bayesian network modeling. First, we gather data from the Workload dataset, which includes physiological measurements such as heart rate, skin temperature, and galvanic skin responses, as well as RR intervals obtained from wearable sensors. Additionally, we incorporated demographic details like age and experience level, as well as contextual factors, including the specific workload experienced during UV operation. This diverse range of data sources ensures that our model captures all contributors to cognitive workload, providing a comprehensive view of the operator state. Next, we apply several machine learning models to classify cognitive workload values based on the physiological data. We tested four models: naive Bayes, XGBoost, logistic regression, and multi-layer perceptron. These models were trained using different preprocessing techniques such as normalization, standardization, and principal component analysis to optimize feature representation and enhance model performance. Our goal was to find the right balance between model complexity and real-time applicability. XGBoost paired with principal component analysis emerged as the best performing model, achieving an accuracy of 69.4%. Finally, we integrated the machine learning results into a Bayesian network to model causal relationship between different variables. The Bayesian network provides a dynamic assessment of cognitive workload risk by considering changes in physiological and environmental conditions in near real time. Unlike traditional classification models, the Bayesian networks helped us understand the causal links between different factors, allowing us to predict overall conditions before they occur. This deeper understanding enables us to implement proactive measures such as altering task allocation, reducing operator stress, or providing real-time feedback to maintain optimal performance levels. Compared to previously reported results for the original Workload dataset, which had an accuracy of 68.2%, our implementation with XGBoost and principal component analysis showed notable improvements. These enhancements make XGBoost a promising candidate for real-time cognitive workload assessments in UAV operations. Moving forward, we believe that leveraging advanced deep learning techniques could further improve accuracy, robustness, and latency, particularly in dealing with more complex scenarios involving high-dimensional and noisy data. In addition to cognitive workload classification, we developed a risk assessment model to detect, evaluate, and mitigate the risks associated with cognitive overload in UV operators. This risk model integrates machine learning outputs with a Bayesian network to enable continuous cognitive workload monitoring and proactive risk management. The model evaluates cognitive overload risk through three main components. First one is threat. This component represents the probability of cognitive overload based on real-time physiological and environmental data. It helps identify when an operator is likely to experience high workload levels that could impair performance. Second one is vulnerability. This component represents the likelihood that the detection system may fail to identify cognitive overload. This failure could result from sensor limitations, data quality issues, or inconsistencies in the learning algorithms. By understanding these vulnerabilities, we can make improvements to the system resilience. And final one is the consequence. This measures the potential impact of if cognitive overload goes undetected, evaluates the severity of mission outcomes, such as decreased performance, increased error rates, or complete task failure. By quantifying these consequences, we can prioritize interventions and allocate resources more effectively to mitigate significant risks. The Bayesian network framework enables dynamic updates to the risk assessment by incorporating new real-time data as it becomes available. For instance, elevated heart rate and skin temperature, combined with stressful environmental conditions, would lead to a higher risk assessment for overload. So this framework provides a means for immediate interventions, such as by providing real-time by reassigning tasks, which ultimately helps in improving both operator safety and mission outcomes. Moreover, the interoperability of the Bayesian network framework makes it valuable not only for real-time monitoring, but also for training purposes. It helps mission planners and operators understand the various factors contributing to cognitive overload, which can be useful for training new operators or refining operational procedures. Our study demonstrates that integrating machine learning with machine learning reasoning significantly enhances the accuracy, interpretability, and reliability of cognitive workload assessment for UAV operators. This approach allows for near real-time detection and prediction of cognitive overload, which is critical in UAV missions where rapid decision-making and situational awareness are crucial. By balancing pattern recognition through machine learning with causal inference using Bayesian reasoning, our model offers a comprehensive understanding of workload dynamics, enabling a more targeted approach to maintaining optimal operator performance. Future research will explore alternative probabilistic frameworks to address uncertainties that may not be fully captured by the current Bayesian network. Also, we plan to develop a digital twin for UAV operators, which would provide a real-time virtual model for the operators of the operator. This digital twin would allow us to predict cognitive workload levels more accurately and provide personalized interventions based on the operator's unique characteristics and historical data. Such a system could significantly improve the effectiveness of cognitive workload management strategies. And furthermore, we aim to expand our dataset to include more diverse real-world flight scenarios to improve model accuracy and make our solution more generalizable to the different environments and stresses. By incorporating varied scenarios, we can better understand how different environmental and operational factors impact cognitive workload, refining our predictive capabilities and enhancing the overall robustness of our model. Ultimately, our research presents a scalable, adaptive model for cognitive workload assessment that supports UAV operators in high-stakes environments. By enhancing safety, performance, and decision making, we are committed to refining this AI framework to ensure that UAV operations meet the highest standards of reliability and efficiency. We envision our system as a key tool for improving operator training, mission planning, and real-time work management, ultimately contributing to the overall success of UAV missions. We acknowledge the support of the Nature Science and Engineering Research Council of Canada. Dr. Rishevsky also acknowledges partial support from the National Science Foundation, ground number OISE 2415299. This material is based upon work supported by the National Science Foundation under grant. Thank you for your attention. I'm happy to answer any questions about our approach, methodology, or future directions. I also apologize for any noise you may have heard. There is an air alert in Ukraine right now, and I hope that everything remains safe, primarily to Ukraine and to our air defense forces for protecting us.